Picture a galaxy so strange, so wildly improbable that the very laws we believed governed cosmic creation collapse at first sight. A radiant golden heart suspended in the void, encircled by a pristine ring of sapphire stars divided by an immense gulf of nothingness. This cosmic enigma has a name, Hoag's object, and it might be the strangest galaxy we've ever discovered. Hoag's object is a galaxy located 600 million light-years away, characterized by a golden core surrounded by a ring of blue stars with a large empty void separating them. Its structure challenges established theories of galactic formation due to its high degree of symmetry and distinct star populations. In 1950, American scientist Arthur Hoag first observed this faint object using the 48-inch Schmidt telescope at Palomar Observatory. On a photographic plate, he noticed a bright circular ring around a small, dense center. He initially considered that it might be a planetary nebula, a glowing gas ring from a dying star, as many have a round shape. However, he noted inconsistencies. The ring was exceptionally large and bright, and the central core resembled a compact galaxy. Hoag proceeded with caution, as astronomers at the time lacked modern telescopes and computers, relying instead on photographic images and brightness measurements. He recorded the object's location in the constellation Serpens and its unusual structure in a 1950 paper, describing it as either a ring-shaped galaxy or possibly a planetary nebula, which marked the beginning of its mystery. Over the following years, photographic plates of Hoag's object became a subject of interest for astronomers. Its structure was a stark contrast to more common, irregular spiral or elliptical galaxies. The ring's clean symmetry led some to speculate it was an optical illusion or a photographic defect. It was not until the 1960s and 1970s, with the advent of better telescopes and advanced spectroscopy, that its true nature began to be understood. Measurements of its redshift confirmed it was a galaxy approximately 600 million light-years from Earth, which meant the ring itself was immense, spanning tens of thousands of light-years. In comparison, planetary nebulae are only a few light-years across. Arthur Hoag had not been searching for unusual galaxies, as his research focused on other celestial structures, making his discovery of this long-standing puzzle. Serendipitous early photographs also revealed that the space between the bright ring and the central core appeared unusually empty. Typically, galaxies exhibit a gradual transition from the core to the outer regions, with stars and gas filling the intervening space. In this case, the intermediate area seemed to have been cleared. During the 1980s and 1990s, improved ground-based telescopes and CCD imaging further clarified that Hoag's object did not fit into standard galactic classifications. It was not a spiral galaxy, as it lacked arms, a bar, or a visible disk. It also did not fit the elliptical category, as its outer ring was too bright and sharply defined. Furthermore, it differed from other ring galaxies, which typically show evidence of violent collisions such as debris streams and irregular ring shapes. Hoag's object, however, showed no signs of disturbance, such as tidal tails or scattered star clouds, which are common indicators of galactic mergers that are thought to form such rings. The Hubble Space Telescope provided a high-resolution image of Hoag's object in 2002, confirming its known features. The image showed a dense, golden oval core surrounded by a nearly perfect blue ring of young, hot stars. Between the core and the ring was a dark space with almost no visible stars. The Hubble image also revealed a smaller, similarly shaped ring galaxy in the background, a coincidence that deepened the object's mystery. For Arthur Hoag, who retired before the full significance of his find was recognized, the discovery became an unexpected legacy. The object that began as a faint anomaly on a photographic plate evolved into a well-known case study in extragalactic astronomy. The nearly perfect ring of Hoag's object is a shape not expected in galaxies. While galaxies are often depicted as orderly spirals or smooth ellipses, they are typically more irregular. Spiral arms can be disjointed, and elliptical galaxies can be uneven. Ring galaxies themselves are often bent, broken, or twisted. The outer structure of Hoag's object is a smooth, continuous loop of bright blue stars, and measurements of its circularity show almost negligible deviations. This level of precision is highly unusual in astronomy, where forces such as gravity from nearby galaxies, the pull of dark matter, and the processes of star formation tend to disrupt order. Ring galaxies are generally thought to form when one galaxy passes through another, creating ripples of star formation. The Cartwheel Galaxy serves as a classic example with its sprawling, uneven structure and scattered knots of young stars. In contrast, the ring of Hoag's object lacks the asymmetries indicative of a collision, such as tidal tails of gas and stars' distortions or lopsided regions. Another notable feature is the uniform width of the ring. In many ring galaxies, star-forming regions cluster together, creating brighter areas, but the width of the ring in Hoag's object is remarkably consistent. Its brightness is also smooth from one side to the other. This high degree of order presents a scientific challenge, as the chaotic forces that shape galaxies would not be expected to produce such a structure. Some scientists have proposed that the symmetry could be maintained by an orbital resonance, where the paths of stars and gas are locked into a stable pattern, similar to how Saturn's moons maintain the sharpness of its rings. However, Hoag's object has no visible companion, galaxies close enough to exert such a sculpting influence. Another unusual aspect is its orientation. From our viewpoint, the ring is almost perfectly face-on, a statistically rare perspective. For observing galaxies, astronomers have used computer models with various starting conditions, including collisions and gravitational resonances, to simulate the ring's formation. These models almost invariably produce rings that are slightly oval, have uneven brightness, or are filled with debris, none of which match the perfection of Hoag's object. The study of light from different parts of the ring reveals that the motion of its stars follows an unusually uniform pattern with consistent orbital velocities across the entire structure. This indicates the symmetry is not merely visual, but is also integrated into the motion of the stars. Such consistency raises challenging possibilities. One explanation is that the galaxy's prolonged isolation has allowed its structure to stabilize without external interference. However, over millions of years, it should have been distorted by internal factors, such as the uneven pull of its own gravity. An alternative theory is that the ring is cosmically recent and has not yet been disrupted. This view, however, lacks evidence of the formative event. Some astronomers have commented, partly in jest, that it appears too perfect, as if engineered. While there is no evidence of anything artificial about Hoag's object, the remark highlights how out of place it seems among the universe's typically chaotic formations. The perfect shape of its ring makes it distinctive among galaxies, possessing a structure so orderly that it can appear unnatural. As far as we know, it remains a cosmic puzzle in the form of a perfect loop. At the center of Hoag's object is a dense golden sphere of stars resembling a small elliptical galaxy, which is nearly as improbable as the ring that encircles it. Although less prominent than the bright blue ring, the core contains most of the galaxy's visible mass. Its color indicates that its stars are very old, much older than those in the surrounding ring, and emit a warmer light. Elliptical galaxies are characteristically collections of older stars compacted into a rounded form, often resulting from ancient mergers, and they typically contain little gas or dust, limiting new star formation. The core of Hoag's object aligns with this description, yet it is situated within one of the most vibrant and star-forming blue rings. Observed, the contrast between the inactive core and the active outer ring is one of its most significant peculiarities. Spectroscopic studies confirm that stars in the core are on average billions of years older than those in the ring, suggesting the core existed long before the ring formed. This raises the question of what process surrounded an old elliptical core with such a young dynamic structure. The core itself is unusually smooth, lacking any dust lanes, gas clumps, or irregular patches. In many galaxies, even old elliptical cores exhibit evidence of past mergers, such as faint shells ripples or stellar streams. This golden sphere, however, is pristine. If a collision created the ring, it is unclear why the core shows no visible damage. Furthermore, the core's light profile, the way its brightness changes from the center outward, is more concentrated than expected for its mass, as if compressed long ago, though there is no sign of recent gravitational compression from a collision. One possibility is that the core is the remnant of a small elliptical galaxy that interacted with a larger spiral galaxy, triggering the ring's formation, before losing its own outer stars. This fails to explain the exceptionally clean result of such an interaction. Another idea suggests the ring, formed from gas captured from a long-lost companion galaxy, which was then pulled into orbit around the core. In that scenario, the gas would have needed to settle into an exceptionally stable and uniform orbit, a hypothesis that is difficult to substantiate. The core's golden light also offers a chemical clue. Its stars are richer in heavy elements, a property astronomers refer to as metallicity, which indicates that the core underwent multiple generations of star formation in the distant past. The chemical enrichment levels in the core do not match those of the outer ring, implying the two regions did not share a common star-forming history and almost seem to belong to two separate galaxies that have merged. Perhaps the most surprising feature of the core is its lack of rotation. It moves less rapidly than predicted, while many galaxies, including older ones, retain measurable spin from their formation. The ring of Hoag's object spins much faster than its core. This discrepancy suggests the two components may have had different origins and are now joined in a stable configuration. Astronomers have tried to model how an old elliptical core could stay so undisturbed while being encircled by a perfect ring, but most simulations fail. The event that creates the ring, like a collision, should also disturb the core. The smoothness of the golden core suggests either that the ring formed through a non-violent process, or that any disturbance occurred so long ago that the core has had time to relax back into its current shape. The contrast between its two main components, a warm golden sphere of old starlight and an electric blue ring like a luminous crown, makes Hoag's object one of the most striking galaxies known. A strange dark gap separates them, and they appear to maintain a distinct distance from one another. This void is one of the object's most perplexing features. Between the core and the ring lies a wide, largely empty region, tens of thousands of light-years across, in galaxies with clear structural divisions. The spaces between major features usually contain scattered stars, star clusters, or faint gas clouds. This area, by contrast, is almost entirely empty. The cleanness of the gap was a surprise in early detailed observations. Deep images from the Hubble Space Telescope confirmed that the void is not an illusion caused by dim stars, but a genuine scarcity with a star density far lower than predicted, as if the area had been swept clean. In a typical ring galaxy formed by a collision, such as the Cartwheel Galaxy, the space between the core and ring is filled with turbulent remnants like stellar streams, gas clumps, and chaotic debris. Hoag's object, however, appears as if an invisible boundary separates the two regions. One explanation is that orbital mechanics maintain the gap. If the gas and stars in the ring follow highly stable synchronous orbits, they might naturally avoid the space near the core, similar to how Saturn's shepherd moons clear gaps in its rings. Yet in Hoag's object, no such shepherding body is apparent. Another theory posits that a past, powerful event cleared the region, perhaps an energetic outburst from a central supermassive black hole that expelled gas and halted star formation in the vicinity. The problem with this idea is the lack of current evidence for an active galactic nucleus. There is no bright central source jets or unusual X-ray activity. Chemical studies of the few stars detected within the gap add another layer to the mystery, as their chemical signatures match neither the core nor the ring. They seem to be relics from an even earlier epoch, suggesting this area may be a fossil zone from a structure that existed before the ring formed. This raises the question of whether Hoag's object was once a different type of galaxy that was somehow transformed. The emptiness also presents a gravitational puzzle. The mutual forces between the core and ring should over millions of years cause stars and gas to drift and gradually fill the void. The fact that the gap remains sharp suggests a stabilizing mechanism is at work. Models that attempt to simulate this stability often require finely tuned conditions that seem unlikely to occur and persist naturally over such long timescales. The gap between the components of Hoag's object contributes to its unusual appearance. The golden sphere of old stars does not gradually fade into the surrounding ring. Instead, there is a distinct and sharp separation. This clear delineation gives the galaxy an artificial quality, as if it were constructed rather than having evolved naturally. While no serious expert suggests it is not a natural formation, its appearance is unsettlingly precise. In a universe where chaos is typical, this order is conspicuous. The gap complicates our understanding of how galaxies transport matter, evolve, and maintain their structures. If the ring and core possess different origins, formed at separate times or from different materials, the gap might represent a permanent boundary between them, a region that has remained unsettled for hundreds of millions of years. Current telescopes cannot fully resolve the contents of this void. It could contain faint streams of dark matter that are undetectable by our instruments, but hold the region together without emitting visible light. Alternatively, it might be a gravitational dead zone, where the conditions for star formation have been absent for eons. Regardless of its nature, this empty space is as defining a feature of Hoag's object as its ring and core, representing a mystery in negative space. The bright blue ring of Hoag's object is not just a visual feature, but also a scientific puzzle. Ring structures are uncommon in space, and those that exist typically have a clear formation history. Most are remnants of significant events, such as a smaller galaxy colliding with the disk of a larger one, which creates expanding waves of dust and stars. Others result from gravitational resonances, which gradually shape stellar orbits into repeating patterns. Hoag's object does not conform to these established models. The initial hypothesis was a collisional ring scenario where a smaller galaxy would have passed through the core of the main galaxy, compressing gas and triggering a ring of star formation. However, this model is inconsistent with observations. Every known collisional ring shows evidence of the impact, such as scattered cosmic debris, variations in the ring's thickness, and the presence of the intruder galaxy nearby, or in the process of merging Hoag's object, exhibits none of these characteristics. Its ring has a uniform shape and consistent width, and there is no obvious nearby galaxy that could have caused the event. Another possibility considered was the resonance ring model, where stars and gas in spiral galaxies become trapped in specific orbital patterns by the gravity of a central bar structure accumulating into rings over millions of years. This model is also unsuitable, as Hoag's object lacks a bar or the spiral arms where such resonances typically form. Its core is elliptical, smooth and rounded without the necessary disk structure for this mechanism to function. Some astronomers proposed that the ring could have formed through the slow accretion of gas from the galaxy's surroundings. In this cold accretion model, streams of intergalactic gas could have spiraled inward, settling into a rotating disk far from the core where stars eventually formed. While this could account for the absence of a visible collision, it does not easily explain how the incoming gas would form such a perfect uniform ring without first creating more irregular structures. A more unconventional idea suggests the ring's symmetry might be due to a particularly smooth and round dark matter halo, the unseen mass surrounding the galaxy. If the dark matter were distributed in a specific way, it could guide gas and stars into a stable orbit. However, mapping dark matter halos is extremely difficult, and there is no direct evidence that the halo of Hoag's object is unique in this manner. The age difference between the core and the ring adds another layer of complexity. Observations indicate that the core stars are ancient, whereas the ring stars are significantly younger, suggesting the ring was a later addition to the galaxy. In a collisional model, the timing would need to be very precise. The collision would have to be recent enough for the ring's stars to be young, yet long enough ago for the ring to achieve perfect symmetry. The motion of the ring also presents a challenge. Spectroscopic data show that the stars in the ring orbit in a highly ordered fashion, with little variation in their velocities. They move not only in the same general direction, but also in nearly identical circular paths, a level of consistency rarely produced by models of ring formation. Typically, a formation event is followed by millions of years of turbulence, but this ring appears stable and mature. Researchers have explored less conventional explanations. One speculative theory is that Hoag's object is the result of a gentle merger where a small galaxy was absorbed so slowly and evenly that it left no chaotic traces, instead contributing its material to form a stable ring. Another hypothesis, though purely theoretical, is that gravitational waves from an ancient event might have triggered star formation in a perfect shell around the core. Each theory addresses some aspects of the mystery, but introduces new questions. The collision model explains the ring's existence, but not its perfection. The resonance model accounts for symmetry, but requires a bar that is not present. Gas accretion explains the young stars, but not the lack of irregular patterns. The dark matter hypothesis remains unproven. Consequently, the formation of Hoag's object remains a significant enigma in extragalactic astronomy. The galaxy seems to defy classification, existing in a quiet region of the universe with a structure that should not be stable, but clearly is. When observing a ring-shaped galaxy, astronomers' first line of inquiry is evidence of a past collision, as most known ring galaxies are formed by the head-on impact of two galaxies. In the standard model, a smaller galaxy passes through the disk of a larger one, creating outward propagating waves of gas and stars that form a ring. These waves trigger new bursts of star formation, illuminating the outer loop. This is a well-established model observed in systems like the Cartwheel Galaxy, whose ring is patchy, uneven, and surrounded by wisps of scattered material, all indicators of a violent history. However, this model does not align with the features of Hoag's object, which lacks every expected sign of a collision. First, there is no visible debris. A galactic collision gravitationally ejects material into space, creating tidal tails, faint stellar streams, and distorted shapes. Hoag's object has none of these. The surrounding space is remarkably clean, which suggests either that no collision occurred or that it happened so long ago that all traces have dissipated, a timeline that contradicts the youth of the ring's stars. Second, there is no identifiable impactor. In most ring galaxy systems, the intruder galaxy is either still in the vicinity or is merging with the core. Hoag's object is relatively isolated. The nearest major galaxies are too distant to be recent impactors, and deep sky surveys have not found any small, stripped-down remnant that could be the remains of an absorbed intruder. Third, the symmetry of the ring is too perfect. Collisions are inherently chaotic, and an off-center impact, which is the most likely scenario, typically results in a lopsided ring. The ring of Hoag's object, however, is almost mathematically circular. A collision would have required an impact so precisely centered that the odds are exceptionally low. The velocity data also present a problem. In known collisional rings, the stars and gas often exhibit a wide range of speeds as the system settles. The ring of Hoag's object, in contrast, shows a surprisingly uniform rotation pattern, suggesting a stability that would not be expected shortly after a violent collision. This implies either that the ring settled into perfect order with extraordinary speed, or that it was not formed by a collision. An alternative possibility maintains the collision theory, but with a unique modification: a ghost intruder scenario in which a very small gas-rich galaxy collided with the core and its material assimilated seamlessly into the existing gas disk. A gaseous intruder should leave visible gravitational signatures, such as changes in the motion of stars in the core. However, the core of Hoag's object is remarkably undisturbed. Another possibility is that an impact occurred not between two galaxies, but between Hoag's object and a large gas cloud. This type of collision could theoretically produce rings instead of the typical stellar debris. This raises the question of the current location of that gas cloud and how it could have distributed the material so uniformly. Observations indicate no large reservoir of gas is floating nearby. Due to the lack of evidence for a collision, many scientists are reluctant to classify Hoag's object with the Cartwheel Galaxy or other known ring systems. Its appearance, behavior, and environment are too dissimilar. If the impact model is insufficient, it suggests that either a significant factor has been overlooked or Hoag's object represents an entirely different mode of galactic evolution. What distinguishes Hoag's object is not only its perfect ring, an unusual core, but also its location in a very sparse region of the universe. Galaxies are typically gregarious. They congregate in groups, exert gravitational forces on one another, and sometimes collide or merge. Although these interactions are disruptive, they drive galactic evolution by redistributing gas, triggering star formation, and altering structural shapes. In contrast, Hoag's object appears to have been isolated for a very long time. When astronomers map its surroundings, they find a surprising absence of nearby galaxies. Hoag's object is located far from any major galaxy cluster. Its closest significant companions are millions of light-years away, too far to have any strong gravitational effect. The space around it is characterized by emptiness, punctuated only by faint distant galaxies in the background. In galactic terms, it inhabits a low-density environment, distant from the crowded centers where galaxies frequently interact. This isolation is significant because it eliminates many of the usual triggers for dramatic galactic change. In denser areas, galaxies are continuously disturbed by tidal forces from their neighbors. Gas flows in and out, collisions are common, and gravitational harassment can alter their forms. Without these influences, a galaxy's structure can stay stable for billions of years. This might explain how the perfect ring of Hoag's object has endured without being disrupted, as there are no nearby objects to disturb it. Isolation also presents difficulties for standard models of ring galaxy formation. The immense distance of Hoag's object from other galaxies makes conventional explanations involving collisions or tidal interactions much less plausible. There is no apparent partner that could have formed the ring through a direct collision or a close flyby. Even if such an event occurred in the distant past, the intruder would have had to depart without leaving a visible trace, which is difficult to align with our understanding of galactic dynamics. The absence of disturbances in its surroundings also complicates the youth paradox. The stars in the ring are not very old, which implies the structure formed relatively recently in cosmic time. Yet if no galaxy has been close enough in recent cosmic history to trigger it, the cause of such a large circular burst of star formation remains unknown. Some experts propose that the location of Hoag's object in a low-density region, sometimes called a cosmic void, may have influenced its development in a more subtle manner. In these underpopulated areas, intergalactic gas can accrete more smoothly without being stripped or heated by frequent interactions. This gas could theoretically be funneled into the galaxy uniformly from multiple directions, settling into a symmetrical circular orbit to create the ring. However, the mechanics of such a process are largely speculative, and models have not yet been able to replicate it successfully. The remoteness of Hoag's object might also account for its pristine appearance. In dense galaxy clusters, a newly formed ring would likely be distorted within a few 100 million years by the gravitational pull of nearby giant galaxies. Hoag's object may have had the opportunity to evolve in near-complete peace, allowing its unique structure to remain fixed without external interference. This isolation could also explain its seemingly unaffected core. Without nearby disturbances to agitate it, or new material to accrete, the core could remain smooth, dust-free and stable for billions of years. This would make it a well-preserved remnant from an earlier era of galactic history, encircled by a ring that formed much later through an unidentified process. The quiet location of Hoag's object does not resolve the central question of its ring's origin. Its isolation exacerbates the problem by removing the most common explanation. This situation is analogous to observing a perfectly circular ripple in a pond with no visible stone sticks or fish nearby to explain its origin. The cause must have been something other than a nearby galactic event. Astronomers persist in surveying the area around Hoag's object for faint evidence of past interactions, such as a faint stream of stars far beyond the ring, or a barely detectable dwarf galaxy that might be the remnant of a former partner. To date, this search has yielded no conclusive findings. When the Hubble Space Telescope captured its high-resolution images of Hoag's object in 2002, astronomers and the public were captivated by its beauty. An even greater surprise was a smaller, fainter ring-shaped object visible in the same frame, located far in the background within the outer ring. This object, sometimes called Hoag's twin, or the smaller Hoag, gives the impression of the universe repeating itself at two different scales along the same line of sight. The inner twin is not associated with Hoag's object. It is a much more distant galaxy. The two will never interact. Their apparent similarity is due solely to a perfect alignment from our perspective. The probability of such an occurrence is extremely low. The background twin is visible through the space between the golden core and the blue ring of Hoag's object. This placement appears almost deliberate, like a design choice in cosmic art. Had the smaller ring been positioned just a few arc-seconds differently, it might have been overlooked. Instead, it is perfectly framed, a smaller version of the main structure, seen through the void. Due to its great distance, the background twin is much more difficult to study. Even with Hubble's resolution, it is just a small smudge of light, clear enough only to suggest a ring-like form. Spectroscopic analysis is challenging, but initial observations imply it might also be a ring galaxy, although its appearance could be due to gravitational lensing or another effect. Its precise nature is still unconfirmed without more detailed data. It has been proposed that the smaller Hoag might not be a genuine ring galaxy. It could be a galaxy viewed through a region of dust or gas that obscures its center, giving the illusion of a ring. However, its brightness distribution tends to support the idea of a real outer structure. If this is correct, it means we are observing two rare cosmic objects aligned by pure chance. Mathematically, the double ring alignment is highly improbable. Ring galaxies constitute a very small fraction of all known galaxies. The likelihood of one ring galaxy being situated directly behind another from our vantage point is exceedingly low. The sight of the two objects has prompted both serious scientific investigation and imaginative speculation. While astronomers concentrate on the mechanics of the alignment and the classification of the background object, it has also captured the public's imagination. Some interpret it as evidence of hidden cosmic patterns or suggest that such structures might be more common if we could observe them at greater depths. For scientists, the background twin serves as a reminder of the role of chance in astronomical observations. If the background galaxy had been slightly off-center, the famous Hubble photograph would have been beautiful, but less remarkable. Instead, the image captures an improbable reality, providing a visual metaphor for the layered nature of the universe. It is also a benefit of observation, as the light from the twin has passed by the foreground galaxy on its way to us. The light from a background object has passed through the ring of gas and possibly the dark matter halo surrounding Hoag's object. In principle, analyzing this light could provide scientists with indirect information about the properties of the material around the galaxy, effectively using the universe as a backlight for an observation that could not be planned. To date, no detailed follow-up studies have revealed more about this background object, primarily because its faintness requires long observation times and access to telescopes is highly competitive. Nevertheless, this alignment is one of the peculiar features that makes Hoag's object notable. It is an exceptionally rare and orderly galaxy, and its most well-known image is photobombed by what could be a distant counterpart visible billions of light-years away. The stellar ages in Hoag's object offer a significant clue to its history, yet they deepen the mystery rather than resolve it. The galaxy's golden core consists of stars that are billions of years old, emitting the warm yellow light characteristic of mature stars. This is expected as elliptical-like cores are typically composed of older stellar populations. The ring, however, is markedly different. Its brilliant blue hue is indicative of young, massive stars that burn hot and fast, some of which are only a few million years old. This significant age disparity is problematic, as galaxies typically exhibit more gradual transitions in their stellar populations, with stars generally becoming younger from the core to the outer edges. In Hoag's object, there is an abrupt discontinuity between the old stars of the core and the young stars of the ring, with the empty gap between them serving as a distinct boundary. It appears as though two different galactic timelines have been superimposed into a single structure. Spectroscopic studies confirm these visual observations. By separating the light from the ring into its constituent wavelengths, astronomers can identify the chemical signatures of different star types and estimate their ages. These studies reveal that many stars in the ring are exceptionally young, less than 10 million years old, while others are several hundred million years old. This suggests that the ring has been a site of star formation for an extended period and remains active today. The core, in contrast, has not produced new stars for billions of years. This raises a fundamental question. If the core is old and quiescent, what is the source of fuel for the ring's sustained star formation? Young stars require dense, cold gas clouds to form, and that gas must have been gathered into the ring through some mechanism. Yet with no nearby galaxies to contribute material and no signs of a recent collision, the origin of this gas remains a puzzle. Some astronomers have proposed that the gas was slowly accreted from the intergalactic medium, the diffuse gas that permeates the space between galaxies. In this scenario, Hoag's object could have attracted streams of pristine hydrogen over hundreds of millions of years, which then settled into stable orbits to form the ring and initiate star formation. While this could account for the continued youth of the ring, it fails to explain its precise circularity. Inflowing gas is typically disordered and would likely lead to warped disks or irregular structures. An alternative theory suggests the age difference is the result of a past interaction that introduced new gas while leaving the core largely undisturbed. For example, a gas-rich dwarf galaxy could have been disrupted, its matter settling into a ring and triggering star formation. This would explain the young age of the ring's stars, but without observable remnant debris or tidal tails, this hypothesis is difficult to confirm. The age paradox also raises questions about timescales. If the ring formed rapidly in a singular event, its stars should have a relatively uniform age. However, the data indicate a spread of ages, implying that star formation in the ring has been a continuous process over a significant period. Whatever mechanism created, the ring did not merely trigger a singular burst, but established conditions for star formation that have persisted for hundreds of millions of years. Furthermore, the chemical composition of the stars in the ring does not perfectly match that of the core. This subtle but important detail shows that the ring stars have slightly fewer, heavier elements, suggesting they formed from gas with a different evolutionary history. This observation strengthens the possibility that the ring's material had an external origin rather than being composed of remnants from the core. The age paradox suggests that Hoag's object contains two distinct histories coexisting within one galaxy, an old quiescent core and a young active ring. They are evolving at different paces, with no apparent connection, either physical or chronological. The effect is analogous to finding a medieval castle perfectly encircled by a modern city's skyline, with no evidence of the intervening historical periods. The galaxy is defined by an absence of spiral arms, a central bar, and any disorder. Although galaxies exist in many forms, they generally adhere to established classifications. Spiral galaxies possess distinctive arms winding around a bright center. Barred spirals feature a central bar of stars that channels material into the arms. Ellipticals are smooth, featureless galaxies composed primarily of old stars. Even irregular galaxies, despite their disorganized appearance, have their own structural logic. Hoag's object, however, defies simple classification. Its most striking structural anomaly is the complete lack of spiral arms. In the local universe, spiral galaxies are the most common type, with most of their star formation occurring in the arms. These arms are shaped by density waves, regions of higher gravity that propagate through the disk, compressing gas to form new stellar clusters. The structures in Hoag's object, by contrast, are not spiral. The object's ring is not an arm curved into a circle. It is a distinct detached circle with no apparent spiral connection to the core. It also lacks a central bar. In barred spiral galaxies, a linear structure of stars extends through the core, acting as a conduit that funnels gas toward the center and influences the galaxy's evolution. Without a bar, this common dynamic is absent. In fact, the core of Hoag's object more closely resembles an elliptical galaxy. It is smooth, round, and devoid of the dust lanes, gas clouds, and star-forming regions typical of spirals. There is also a remarkable lack of asymmetry. Most galaxies, even those that appear symmetrical, reveal asymmetries upon closer inspection. A spiral arm may be brighter on one side, a dust lane might bisect the core, or faint tidal streams from past encounters might extend into space. Hoag's object is devoid of such imperfections. The ring is uniformly luminous, the core is pristine and symmetrical, and the space between them is empty. It is as if every chaotic element associated with galactic evolution has been eliminated. This structural simplicity is puzzling, because galaxies do not typically remain so orderly. Interactions with neighboring galaxies, minor mergers, and the uneven distribution of gas and dark matter tend to induce asymmetries over time. Hoag's object should theoretically exhibit evidence of its past, yet none is visible, even in high-resolution observations. Some researchers have suggested that the absence of spiral arms and a bar could be related to the galaxy's mass distribution. If Hoag's object possesses a particularly stable gravitational potential, perhaps influenced by an unusually smooth, dark matter halo, it might inhibit the formation of the density waves that create spiral arms. However, this does not explain why the outer ring is so perfectly formed while the interior remains void. The absence of a bar is more challenging to explain. Bars tend to form spontaneously as stars within a disk galaxy respond to gravitational instabilities. They are found in both young and old galaxies, suggesting they are a common feature of galactic evolution. If Hoag's object ever possessed a bar, it must have dissolved. Yet the dissolution of a bar typically leaves behind features such as a central bulge or an inner ring, neither of which is present. Another peculiarity is the absence of dust lanes. Spiral galaxies are traced by dark, winding filaments of dust that provide the raw material for star formation. The core of Hoag's object is dust-free, and the ring lacks the patchiness characteristic of dust clouds. This lack of dust may contribute to its clean appearance, but it also implies that the process that formed the ring did not involve the turbulent gas-rich conditions common in spiral galaxies. Collectively, these absences render Hoag's object a structural anomaly, a galaxy that lacks nearly every common galactic feature except for its core and its unusual ring. It defies the standard classifications astronomers use, existing outside the typical spiral, elliptical, or irregular frameworks. It is tempting to view it as a fully evolved galaxy that has settled into a final stable state. However, the active star formation in the ring indicates that it is still an active system. The object is evolving, but not in a way that conforms to standard models, as the forces that shaped it left no conventional traces. The problem lies in its perfect symmetry. Images of Hoag's object reveal an almost perfectly round ring, a feature that is its most prominent characteristic. It is not distorted, stretched, or warped. Its width is uniform, and it maintains a consistent distance from the center from any viewing angle. Such precision is extremely rare in astronomy, as nature seldom produces perfectly circular forms on a galactic scale. Most ring galaxies exhibit noticeable distortions, with some sections of the ring being thicker or brighter due to uneven star formation or residual collision debris. Even in systems with distinct rings, gravitational forces from nearby galaxies or their own uneven mass distribution typically elongate the ring into a slight ellipse over time. Hoag's object shows none of these imperfections. Its symmetry is so exact that astronomers use it to calibrate image processing algorithms. If the software can accurately trace a circle around the ring, it is considered to be functioning correctly. The issue with this perfection is its inconsistency with typical galactic evolution. Rings are dynamic with moving stars, drifting gas clouds, and constant influence from external forces. Even in isolation, a galaxy's internal gravitational fluctuations should induce subtle warping over millions of years. However, the ring of Hoag's object appears to be in a state of geometric purity. To preserve this shape, the galaxy's mass must be distributed with exceptional precision. One hypothesis suggests an unusually smooth and spherical dark matter halo, which would exert a uniform gravitational pull and maintain the ring's stars in stable circular orbits. Yet mapping dark matter halos is challenging, and this has not been confirmed for Hoag's object. Another possibility is that the ring formed from a single rapid event, such as a perfectly aligned impact, and has had insufficient time to deform. This idea is challenged by evidence of star formation in the ring for hundreds of millions of years, which contradicts the expected uneven and transient structure of a short-lived event. Some scientists propose that the uniformity is due to the motion of the stars within the ring. If their orbits are coplanar with minimal irregularity, the ring would appear circular. This raises the question of how so many stars achieved such orderly motion, as stellar movements in galaxies are typically more chaotic. The void between the ring and the core is an additional puzzle. Most galaxies, including those with rings, have some diffusion of stars or gas between their main structures. The gap in Hoag's object is distinct, suggesting the ring occupies a precise orbital distance where other matter is excluded. This clear separation enhances the visual symmetry but complicates the mechanical explanation. Time also presents a challenge, as stable structures tend to lose equilibrium over billions of years due to minor gravitational perturbations, gas flows, and stellar motions. If Hoag's object has maintained its perfect shape for a significant portion of its existence, an active mechanism must be preserving it. It remains uncertain whether this is due to dark matter, orbital resonances, or another unknown force. This perfection is central to the scientific debate. Attempts to explain it with known physics require a choice between maintaining the symmetry or accounting for the star formation within the ring. as the galaxy appears to be a convergence of two seemingly impossible yet concurrent events. Dark matter is an effective scientific tool, invisible but detectable through its gravitational effects. Most galaxies exhibit evidence of dark matter in the motion of their stars and gas, particularly in their outer regions, where visible matter alone cannot account for observed speeds. By comparing a galaxy's visible light to its stellar movements, astronomers can estimate its dark matter content. However, for Hoag's object, the results are not straightforward. Its rotation measurements, specifically the velocities of stars in the ring and core, do not align with patterns expected from a standard dark matter halo. In many galaxies, rotation curves remain flat or rise at great distances from the center, indicating the dominance of dark matter's gravity in the outskirts. Data from Hoag's object suggests otherwise. The ring's stars move slower than anticipated for a galaxy of its size, implying a weaker or atypically shaped dark matter. Halo 1 theory proposes that the dark matter halo of Hoag's object is less dense than usual, meaning it contains less unseen matter relative to its stars and gas. This would be unusual, as ring galaxies are thought to require strong dark matter halos for structural stability. Insufficient dark matter would likely cause gravitational instability, leading the ring to warp or disintegrate over time. Yet the ring of Hoag's object is stable and uniform. It is also possible that the dark matter distribution is unconventional. While many galaxies have a spherical halo with a smooth density that increases toward the center, the halo of Hoag's object might be flatter, less uniform, or have a distinctively sharp edge, which would unusually alter stellar orbits. This could also account for the clear gap between the core and the ring, as an unstable gravitational field in that region would prevent matter from residing there. Some astronomers speculate that Hoag's object might be a case for considering modified gravity theories as an alternative to dark matter. These theories propose that gravity behaves differently at very low accelerations, which could eliminate the need for dark matter in some scenarios. Although controversial, the anomalous rotation profile of Hoag's object is the kind of evidence that prompts testing of these ideas. The issue is further complicated by dark matter's role in gas acquisition and retention. A dark matter halo's gravitational pull typically prevents gas from escaping, thereby sustaining star formation. It is unclear how Hoag's object has collected and retained the gas for ongoing star formation in its ring, if its halo is weak or differently shaped, as the ring might have dispersed long ago without this support. The galaxy's isolation adds to the mystery. As it is not near other galaxies that could influence it, Hoag's object should be an ideal subject for studying dark matter distribution without the complication of neighboring gravitational pulls. Despite this advantage, the data does not conform to standard halo models. The challenge is compounded by its distance of approximately 600 million light-years, which makes obtaining precise velocity measurements difficult, particularly for faint stars in the outer ring. Astronomers use gas cloud movements as proxies, but these measurements can be affected by stellar winds or minor historical perturbations. Future telescopes may provide a clearer understanding of the galaxy's dark matter profile, but current data is inconclusive. By the time the Hubble Space Telescope observed Hoag's object in 2002, the galaxy had already been a subject of scientific interest for over 5 decades. While previous ground-based images were remarkable for their era, they lacked the fine detail needed to uncover its secrets. Hubble's high-resolution observation changed this, instantly producing an image of such clarity and symmetry that it became iconic in the early 2000s and generated renewed interest from both scientists and the public prior to Hubble-Hoag's object was seen as a diffuse core encircled by a faint ring, with its features blurred by Earth's atmosphere. The fundamental structure was apparent, but specific details, like the uniform spacing of stars in the ring, the void of the gap, and the distinct nature of the core, were obscured. Hubble's advanced optics and location above the atmosphere brought these elements into focus for the first time. The 2002 images showed that the ring was not an indistinct band of light, but was instead comprised of thousands of hot, young blue stars concentrated within a narrow area. The combined glow of its stars outlined the ring, creating an appearance similar to a neon halo in deep space. The ring's width was remarkably consistent, and its star clusters were distributed evenly with no clumping or visible disruptions. The core was also sharply defined, appearing as a smooth golden sphere of older stars rather than a disorganized central bulge. It lacked dust lanes, obvious star-forming regions, and irregularities that might suggest recent turbulence. This smoothness contributed to the captivating quality of the Hubble image, giving the galaxy a look of almost manufactured perfection. One of the most surprising features revealed in Hubble's picture was a smaller, more distant ring-shaped galaxy perfectly aligned in the space between the core and the outer ring. This faint background object duplicated the structure of Hoag's object in miniature, creating the impression of a double-ring galaxy. The statistical unlikelihood of such an alignment contributed to the image's widespread online popularity. Beyond their beauty, the pictures provided useful information for experts. Astronomers could refine predictions of stellar ages by examining the colors of the stars in both the core and the ring. The yellow tones in the core indicated older, cooler stars, while the bright blue light in the ring signified massive, short-lived stars only a few million years old. The significant difference in age and color deepened the mystery of how the two structures formed and evolved. The level of symmetry in the Hubble images also enabled the testing of theories about the galaxy's formation. For example, if the ring had resulted from a collision, astronomers would expect to find signs of distortion, uneven star formation, or faint tidal debris. None were present in the high-resolution data. This absence of expected features led some researchers to consider alternative explanations like resonance patterns or unusually stable gravitational environments. Hubble's study did not solve the puzzle of Hoag's object, but rather brought it into sharper focus. The clean lines and flawless geometry forced scientists to recognize how rare such a structure is. Many proposed scenarios were invalidated because they could not produce such a perfect form without leaving behind telltale scars. The images also had a cultural impact, featuring in astronomy, outreach programs, textbooks, and internet forums, where they were often used to illustrate the beauty and strangeness of the universe. For many people previously uninterested in galaxies, its symmetry was astonishing. For some, Hoag's object was their first introduction to the idea that objects in space can be both natural and remarkably beautiful. The mystery of Hoag's object is centered on the invisible halo of gas that encircles the galaxy rather than its bright blue ring or golden core. Scientists have detected a large region of hydrogen gas that extends far beyond the outer ring. Although faint, it is measurable by sufficiently precise radio telescopes. While many galaxies have gas halos, the behavior of the ring in Hoag's object is unexpected. In most galaxies, particularly those with active star formation, the gas halo is dynamic, with streams flowing inward to fuel starbirth. and other streams being pushed outward by stellar winds, supernova explosions, or central black hole activity. These inflows and outflows create a patchy, turbulent halo structure with compressed hotspots and voids. By contrast, the halo of Hoag's object appears remarkably smooth and undisturbed. The gas halo shows no obvious signs of motion toward or away from the galaxy. Spectroscopic studies that measure the Doppler shift of hydrogen emission lines find very little net movement, which means the gas is neither clearly feeding the ring's star formation nor being ejected in powerful flows. It appears to exist as a calm extended bubble around the galaxy. This presents a problem for models of how galaxies sustain star formation. The outer ring of Hoag's object is actively producing young, massive stars, which requires a steady supply of dense cold gas. If the halo is not supplying this gas, the source of the fuel is unclear. Some astronomers speculate that small amounts of gas may be trickling in too subtly to detect directly, but even this would necessitate an unusually stable transfer process to avoid disturbing the halo's shape. The size of the gas cloud is another unknown. Estimates indicate it extends to 2 or 3 times the diameter of the galaxy's main visible structure. It is not clear how an apparently isolated galaxy acquired such a large gas reservoir without tidal interactions from nearby galaxies. The halo's smoothness also suggests an absence of recent violent events. In many galaxies, mergers or close encounters leave distinct marks in the gas distribution, such as streams, shells, or irregular clumps. The halo of Hoag's object lacks these features, suggesting it has not been significantly disturbed for hundreds of millions of years. This stability may help preserve the ring's perfect symmetry, but it also makes the galaxy difficult to explain through typical ring formation scenarios, which usually involve a disruptive event. Some researchers have proposed that the halo could be a remnant from an earlier stage in the galaxy's life, perhaps left over from when the ring itself formed. If a massive inflow of gas from a merger, a captured gas cloud, or a resonance effect created the ring, the leftover material could have spread outward to form the current halo, with chaotic elements settling over time. This, however, raises the question of why more of that gas has not fallen inward to fuel more star formation. The halo's unusual behavior might also be related to the distribution of dark matter in Hoag's object. A smooth, spherical dark matter halo could help stabilize the gas envelope by distributing gravitational forces evenly. This might hold the gas in a state of equilibrium between gravity and pressure, preventing it from collapsing inward too quickly. In astronomy, metallicity measures the abundance of elements heavier than hydrogen and helium in a star or gas cloud. These heavier elements, termed metals in astrophysics, are forged inside stars and distributed into space when they die. Over cosmic time, successive generations of stars enrich a galaxy's gas with more metals. Consequently, older stars generally have lower metallicity, while younger stars tend to form from metal-rich gas. Hoag's object, however, does not strictly follow this rule. Studies of its ring's metallicity have revealed that the young blue stars in the outer ring possess a chemical composition that would not be expected if they formed from the core's enriched material. Their metallicity is significantly lower than that of the core stars, resembling the chemical signature of gas, with a very different evolutionary history. This is significant because it indicates the ring was not formed by pushing gas outward from the interior. If that were the case, the gas in the ring would also be high in metals, having originated from the same source. The low metallicity instead points to an external source of new gas. It is possible that Hoag's object captured a large cloud of nearly pure hydrogen from intergalactic space, which would explain both the lower metallicity and the ongoing star formation in the ring. It is difficult to explain, however, how such a large amount of gas could be captured without leaving clear signs of disorder, such as tidal tails, asymmetries, or debris. Another concept is that the ring may be the remnant of a gas-filled dwarf galaxy that Hoag's object consumed. In this scenario, the dwarf's gas settled into a ring around the core and began to form stars. This could be consistent with the observed chemistry, as smaller galaxies tend to have lower metallicity than larger ones. Yet this idea is not supported by sufficient data. The stars from such a dwarf are not visible, and the ring's perfect symmetry is inconsistent with the usual appearance of merger remnants. The metallicity puzzle becomes more interesting when considering the distribution of metals within the ring itself. Observations show that the metallicity is relatively uniform all the way around, rather than being patchy or showing gradients. In most galaxies, metallicity tends to vary with location, reflecting the complex history of gas flows, star formation, and supernova feedback. The ring of Hoag's object appears remarkably uniform, suggesting the gas that formed it was thoroughly mixed before star formation commenced. This degree of chemical homogeneity is difficult to attain without turbulence or rotational mixing. Yet the ring shows no signs of being disturbed by violent processes. This implies a gentle and controlled settling of gas into the ring, which contradicts the high-energy events typically used to explain ring formation. Another issue arises from the metallicity data. While the stars in the ring are less metal-rich than those in the core, they are not metal-poor. They contain heavier elements such as oxygen, nitrogen, and iron, indicating that the gas they formed from had already undergone at least one cycle of stellar evolution. This rules out the possibility that the gas is primordial or unchanged since the Big Bang, but leaves the question of its origin and unusual arrangement unanswered. The disparity in metallicity between the core and the ring may offer clues to the galaxy's age. If the core formed early in the universe's history and expelled most of its gas, it could have remained chemically stable for billions of years. A later influx of less enriched gas could then have formed the ring, giving the galaxy two distinct formation timelines. This idea is consistent with other evidence suggesting the core and ring are morphologically distinct. Galactic scientists typically observe that the central components of galaxies rotate at speeds comparable to their surrounding structures. In spiral galaxies, the bulge and arms rotate in a related manner, while elliptical galaxies tend to move as a single, less organized system. Hoag's object deviates from this norm in a subtle but significant way. Its luminous ring rotates much more slowly than its core. This was determined by measuring the Doppler shifts in the light from stars in both regions. The stars in the ring orbit the galaxy at a velocity consistent with an actively spinning disk. In the core, however, the rotation curve flattens to a near standstill. The galaxy's center appears to move more slowly than its outer structure. This discrepancy is a strong indicator that the core and ring may have separate origins. If the ring had formed as a natural extension of the core's disk, their rotational velocities would be expected to be linked with the core acting as the gravitational anchor. Instead, the ring's faster rotation suggests it may be orbiting not just the core, but the galaxy's larger dark matter halo, with the core having a less dominant role in its dynamics. The core might be the remnant of an older, slower rotating elliptical galaxy. If Hoag's object was initially elliptical and the ring was accreted later, perhaps by capturing an external gas reservoir. The difference in rotation would be logical. The old core would retain its slow rotation, while the new ring would move at a velocity dictated by the larger gravitational structure. The smooth transition from the slowly rotating core to the rapidly rotating ring is another noteworthy feature. In many galaxies with mismatched components, there is an intermediate zone where the two motions interact, creating warped structures or chaotic stellar orbits. Hoag's object lacks this, as the space between the core and the ring is largely empty, providing a clear separation between the two regimes. Their distinct rotations may persist because they are not physically connected enough to synchronize. Over time, researchers have also suggested that the core's slow rotation could be related to its pristine, dust-free appearance. In many galaxies, gas inflows over billions of years increase the core's rotation by adding mass and exerting gravitational torque. Without a continuous supply of gas, the core's rotation can stagnate. The gas supply of Hoag's object seems to be concentrated entirely in its ring and surrounding halo, allowing the core to evolve passively and slowly. The slow rotation also has implications for the galaxy's potential central black hole. The rotation of a galactic core often helps to channel material into its central black hole, fueling energetic outbursts observable across the electromagnetic spectrum. The absence of such activity in Hoag's object, which is unusually quiet at radio and X-ray wavelengths, could be a result of the core's sluggish motion, which fails to deliver gas efficiently to the center. A remaining question is whether the core's rotation has always been this slow. If the ring formed relatively recently, perhaps within the last billion years, there may not have been sufficient time for gravitational interactions to accelerate the core. Over the next few billion years, as the ring and core exert subtle gravitational forces on each other, their motions might begin to align. This would imply we are observing Hoag's object in a rare transitional state between two dynamic phases. The galaxy's unusual isolation may have helped preserve its slow spin, as the absence of nearby galaxies prevents external gravitational forces from altering its rotational momentum. This could allow it to exist indefinitely in this nearly disconnected state, like a relic from an earlier epoch surrounded by a much more dynamic structure. In most galaxies, starbursts, intense periods of star formation, have a clear cause. A collision between a smaller and a larger galaxy can compress gas into dense clouds, initiating the birth of new stars. Alternatively, tidal forces from a close pass by a neighboring galaxy can drive gas inward, triggering a rapid burst of star formation. In Hoag's object, however, the bright blue ring is actively forming new massive stars without any of the usual evidence of a triggering event. Spectroscopic analysis shows the ring is abundant in hot, short-lived O and B-type stars, which burn brightly and die within a few million years. Their presence indicates that star formation in the ring is not only ongoing, but vigorous. Yet astronomers find no typical clues for what initiated this activity. There is no evidence of a recent galactic merger, such as streams of stellar debris, distorted shapes, or asymmetrical clumps within the ring. The galaxy resides in a notably isolated region of space, making a recent encounter with another large galaxy highly improbable. Even the smaller background galaxy visible in the well-known Hubble image is located far behind Hoag's object and has no gravitational influence. This raises the question of the origin of the fuel for this starburst and why it is arranged so perfectly in a ring. One hypothesis is that the star-forming gas has long been part of the ring and is only now condensing into stars. If this were the case, however, the ring should exhibit signs of gas depletion over time, with star formation gradually diminishing. Instead, the activity is uniformly distributed, suggesting a steady replenishment of material. Another possibility is that the ring is a self-sustaining structure. As new stars form and supernovae occur, they can generate shock waves that propagate through the surrounding medium, potentially triggering further star formation in adjacent regions. If the ring's structure naturally channels these shock waves along its circumference, it could create a feedback loop that sustains the process without an external trigger. Still, this does not explain how the ring was initially configured to support such a stable loop. The metallicity of the ring's stars is also a factor. Their relatively low abundance of heavy elements suggests the gas is from an external, less enriched source, or has been largely unaffected by multiple generations of star formation. Low metallicity gas cools less efficiently, making it more resistant to collapsing into stars without an external stimulus. This makes the ring's sustained activity even more puzzling, as if the galaxy has found a method to induce stubborn gas to form stars at a steady rate. Another consideration is the galaxy's dark matter halo. If the halo is exceptionally spherical and smooth, it could provide a stable gravitational environment for the ring, allowing gas clouds to orbit without being disrupted. Over time, minor instabilities or density waves within the ring could gently compress the gas, just enough to form new stars. This process would be gradual and long-lasting, devoid of the violent, short-lived events associated with a galactic collision. An interesting but unverified hypothesis suggests the ring's starburst is caused by an unseen interaction. For instance, a small companion galaxy too faint for current instruments to detect could be passing through the ring and creating compressional waves. Such an object would need to be very dim and precisely aligned to avoid disrupting the ring's symmetry. The ring in Hoag's object may have been formed by orbital resonance. A captivating theory regarding its origin. Resonance occurs when different components of a galaxy, such as the orbits of stars and gas clouds or nearby celestial bodies, interact and synchronize their motions. This synchronization can concentrate matter in specific regions, creating patterns like rings or gaps, similar to how resonances with moons shape Saturn's rings. In galaxies, resonance rings typically arise when an internal rotating bar or spiral pattern applies a periodic gravitational pull on the surrounding stars and gas. Over time, this traps material at orbital distances where the pattern's rotation aligns with the star's orbital periods, causing the material to accumulate and form a ring. The case of Hoag's object is more perplexing. Traditional resonance requires an internal structure, such as a bar or spiral arms, to initiate the process, but Hoag's object lacks both. Its core is a smooth, dust-free sphere with no evidence of an internal bar that could guide gas into a ring. Consequently, the standard resonance ring model does not apply well. Some researchers propose that the resonance was caused by an external factor rather than an internal one. For instance, a small galaxy might have passed nearby long ago, with its gravity creating the circular pattern. If this occurred, the perturbing object would now be gone, with the ring as the sole evidence. This ghost resonance concept is compelling, as it eliminates the need for a persistent bar or spiral pattern, but it is difficult to prove without identifying the responsible body. Another possibility is that the resonance is induced by the galaxy's surrounding dark matter halo. An unusual density profile or a slight imbalance in the halo could alter the orbits of stars and gas, favoring ring formation. This area of study is highly theoretical because dark matter, while invisible, exerts gravitational influence, making it a plausible explanation when conventional theories fail, as with Hoag's object. A significant challenge to the resonance theory is that it generally creates rings with irregularities. Most observed resonance rings exhibit brighter clumps of active star formation or minor variations in thickness. In contrast, the ring of Hoag's object is remarkably smooth and uniform. If resonance is responsible, it has achieved a degree of symmetry rarely seen in other galaxies. Computer simulations have struggled to replicate this outcome. Attempts to generate a ring solely through gravitational resonance in a galaxy with a smooth core typically result in a lopsided or slightly warped structure. Achieving the perfection of Hoag's object in simulations often requires highly specific, finely tuned initial conditions, leading astronomers to question whether this is an extremely rare event rather than a common process. Nevertheless, the resonance theory is still considered because it explains the ring's long-term stability. If stars and gas are in resonant orbits, they can maintain their relative positions for billions of years, preventing the collisions and dispersal that would otherwise degrade the ring's definition. This could account for how Hoag's object has remained so pristine without recent external influences. The theory lacks direct evidence, such as a measurable pattern in the ring star's movements that aligns with resonance model predictions. Future instruments with greater precision and power might detect such a pattern. For now, the resonance theory remains an unproven hypothesis without conclusive evidence. If resonance is the correct explanation, Hoag's object would be one of the most extreme and possibly unique examples of this phenomenon. This would deepen the mystery, as it would mean abandoning another viable explanation for this perfectly formed galactic ring. When astronomers first became aware of Hoag's object in the mid-20th century, an early theory proposed it was not a peculiar galaxy, but an optical illusion created by gravitational lensing. Gravitational lensing occurs when a massive object such as a galaxy or galaxy cluster bends the light from an object behind it, producing arcs, rings, or multiple images. In cases of perfect alignment, a nearly complete circle of light, known as an Einstein ring, can form, with its bright central object surrounded by a perfect ring. Hoag's object resembled one of these cosmic illusions. The hypothesis was appealing. The golden core could be a foreground galaxy, and the blue ring a distorted image of a more distant galaxy whose light was bent around it. This would have provided a straightforward explanation based on well-understood physics, avoiding the need for an exotic or extremely rare galactic formation event. However, the gravitational lensing theory was disproven as astronomers examined Hoag's object more closely. Spectroscopic measurements delivered the first contradiction. Scientists found that the light from both the core and the ring had the same redshift, indicating they are at the same distance from Earth. If the ring were a lensed background galaxy, its redshift would be substantially greater. The data confirmed that the ring and core belong to the same physical structure. The ring's internal features provided further evidence against lensing. While gravitational lensing can magnify and stretch distant objects, it also causes distortion, creating streaks, repeated patterns, or smeared details. In contrast, the ring of Hoag's object contains distinct, evenly distributed, and undistorted star clusters, which is consistent with a direct view rather than one through a gravitational lens. To produce such a perfect, thick and uniform ring through lensing, the central mass would need to be much larger than the small spherical core of Hoag's object. Well-defined Einstein rings are typically formed by galaxy clusters or massive galaxies with extensive dark matter halos, and the core of Hoag's object lacks sufficient mass to bend light on this scale. The empty space between the core and the ring also argued against the lensing hypothesis. An Einstein ring does not require a complete void. Lensed light often spills toward the center. The gap in Hoag's object is genuinely devoid of stars, supporting the idea of a physical starless region, rather than an optical effect. Furthermore, the theory could not account for the galaxy's dynamics. Observations reveal that the ring rotates in a manner consistent with being gravitationally bound to the core. In a lensing scenario, no such dynamic link would exist, as the light from the background galaxy would not move in unison with the foreground object. This shared motion was definitive proof that the core and ring are part of a single galaxy. By the time the Hubble Space Telescope imaged Hoag's object in 2002, the lensing theory was largely abandoned. The high-resolution image revealed the evenly spaced star clusters in the ring, and also showed the faint structure of a different lensed galaxy far behind Hoag's object, demonstrating how a true gravitational lens appears, which is quite different from the galaxy's primary structure. Astronomers observe galaxies in radio wavelengths in addition to visible light. Radio waves can reveal phenomena not visible optically, such as star formation within dense dust clouds, energy jets from black holes, or the distribution of neutral hydrogen gas. Many ring galaxies, particularly those with high rates of star formation, are bright in radio waves due to the energetic processes within them. Hoag's object, however, is unusually quiet in this part of the spectrum. Radio surveys have found only weak emissions from the object, significantly fainter than what would be expected from a galaxy with an active star-forming ring. Typically, massive young stars in such a ring would conclude their lives as supernovae, accelerating cosmic rays and generating strong synchrotron radiation, which is an indicator of vigorous star formation. In Hoag's object, however, the radio brightness is just above the detection threshold. This lack of significant radio output is puzzling. It suggests either that the rate of massive star formation is lower than optical images indicate, or that the supernovae are less efficient at producing cosmic rays. The ring's bright blue color points to a large number of hot, short-lived stars, making the first explanation improbable. This leaves the possibility that the galactic environment is suppressing the sequence of events that results in radio emission. One hypothesis proposes that Hoag's object has a weaker interstellar magnetic field than most galaxies. Much of the synchrotron radiation observed at radio wavelengths is from cosmic rays spiraling along magnetic field lines. If the field is particularly weak, radio emission would decrease even if supernovae occur at a normal rate, as fewer cosmic rays would be captured. Although measuring magnetic fields in galaxies is very difficult, Hoag's object could be a key example of how these fields influence a galaxy's radio emissions. It is also possible that the gas in the ring is distributed in an unusual manner. In many starburst regions, dense pockets of gas and dust confine energetic particles from supernovae, which increases the local radio output. If the gas in Hoag's object is distributed more evenly, these particles could escape into intergalactic space before emitting a significant signal. This theory is consistent with other unusual features of the galaxy, such as the linear gas formation in the halo and the absence of swirling motion in the ring. The low radio emission also extends to the galaxy's core. Many galaxies, even those that are relatively inactive, emit some radio energy from their central black holes, sometimes from low power jets or hot gas near the event horizon. Hoag's object shows no such activity, reinforcing the notion that its core is unusually passive. This aligns with other evidence including its slow core rotation and the absence of dust lanes or gas inflows. Hydrogen line emissions used by astronomers to trace cold gas are also faint in this galaxy. This does not imply a lack of gas, as other observations confirm a large halo is present. Instead, it suggests that much of the gas is either too diffuse or too smoothly distributed to create strong, localized signals. This observation supports the characterization of Hoag's object as a system that is stable to the point of being nearly static. From a broader perspective, the radio silence may indicate that Hoag's object is not only an optical anomaly, but is also abnormal at other wavelengths. Most galaxies that appear this unusual also have strange characteristics when observed with radio waves. This is often because the same forces that shape them, collisions, mergers, and strong gravitational interactions, also generate strong radio waves. It seems that the event that formed Hoag's object was either a rare gentle occurrence or one that happened so long ago that its energetic effects have dissipated. Future radio instruments, such as the Square Kilometre Array, may be able to create more detailed high-resolution maps of the signals from Hoag's object, which could help identify faint, previously unseen structures. These maps are still expected to show only a very faint level of radio energy, which would confirm that this galaxy is truly unique. The core of Hoag's object is distinct not only for its color and slow rotation, but also for its exceptionally clean appearance. The cores of most galaxies even generally calm. Elliptical galaxies show minor irregularities, like faint dust lanes, wisps of gas, or small clusters of stars. These features are signs of internal activity mergers and gas flows that have occurred over billions of years. In contrast, the core of Hoag's object is remarkably uniform. When the Hubble Space Telescope imaged the galaxy in 2002, its resolution was sufficient to reveal fine details across the central sphere. Astronomers expected to find some variations in brightness, indicating dust clouds or younger stellar populations. Instead, the core's surface brightness is almost perfectly uniform, resembling a smooth sphere of ancient stars. There are no visible dust filaments, clusters of blue stars, or signs of recent star formation. This level of uniformity is uncommon because galactic cores are typically complex environments. Gas from outer regions usually drifts inward, fueling bursts of star formation or a central black hole. This process leads to the accumulation of dust, which forms lanes or swirls that disrupt the light. Even in galaxies not undergoing major mergers, minor interactions with satellite galaxies can disturb the central areas. The absence of these signs in the core of Hoag's object suggests an extraordinary degree of long-term isolation. The smoothness also supports the theory that the core is composed of a very old stellar population. Spectroscopic studies show that most of its stars are yellowish, similar to the older stars in elliptical galaxies. If the core has not received a significant inflow of fresh gas in billions of years, new star formation would have ceased, leaving only these ancient, evenly distributed stars. The mystery is not just the core's age, but how it has remained untouched for so long, despite the active star-forming ring around it. In a typical galaxy, material from an outer star-forming disk can drift inward due to gravity and settle in the core. The vast empty gap between the core and ring of Hoag's object, however, seems to act as a barrier preventing gas from migrating inward. Without this flow, the core remains an isolated relic of its initial formation phase. One might question if the smoothness is an optical effect due to our viewing angle. A view down the galaxy's axis might obscure structural features visible from a different perspective. However, the ring's symmetry makes it very likely that we are observing Hoag's object almost exactly side-on, which implies the smoothness is real and not an illusion of perspective. It is also possible that the core underwent a past period of intense activity that completely cleared it out. Strong winds from supernovae or a period of black hole activity could have expelled any remaining gas and dust, leaving only stars. In the time since the core would have had ample opportunity to settle into its current calm, uniform state. The issue with this idea is the absence of any lingering evidence of such an event. There are no ejected shells of gas, shock fronts, or other indicators of the violence that might have produced such perfection. This smoothness is crucial for understanding the galaxy's origins. A core this pristine implies either a very gentle formation process or that any imperfections were smoothed out with great precision a very long time ago. Neither scenario fits well with standard models of galaxy formation and evolution, which predict that some degree of central irregularity is almost always present. From a distance, the outer ring of Hoag's object appears as a bright, smooth loop of stars and gas that seems frozen in place. In reality, the stars in this ring are moving at hundreds of kilometers per second around the galactic center, maintaining a precise gravitational balance. The question is, how such a large, thin structure remains stable for billions of years without disintegrating or smearing into a disk. In most galaxies, especially elliptical ones, stars in the outer regions are part of a flat disk held in place by the gravitational pull of visible matter and a larger halo of dark matter. A ring galaxy like Hoag's object presents further complications. A vast empty space separates the ring from the core, so the ring is not supported by a continuous distribution of stars inside it. Without additional forces to hold them in place, gravity would eventually cause the stars to drift closer together or farther apart, changing the ring's shape over time. A key stabilizing factor is the galaxy's dark matter halo. Observations indicate that Hoag's object is embedded in a massive, roughly spherical halo of dark matter that extends far beyond the visible ring. This halo provides an invisible gravitational framework that keeps the ring's stars in stable, nearly circular orbits. Without this hidden mass, the ring would likely dissolve within a few 100 million years. The ring's smooth rotation provides another clue. Astronomical measurements of Doppler shifts for stars and gas along the ring's circumference reveal highly uniform orbital speeds. In contrast, minor speed irregularities in other ring galaxies can lead to the formation of clumps, warps, or breaks over time. Hoag's object appears to have avoided this outcome, potentially due to an exceptionally even distribution of mass in its core and halo. Such a symmetrical gravitational field would maintain orbital alignment, enabling the ring to stay both stable and perfectly circular. The dynamics of gas also contribute. The ring is composed of both stars and a substantial amount of gas, which has different properties than stars. Gas clouds can collide, merge, and lose energy, causing them to slowly settle into a shared orbital plane. This process can resolve irregularities and assist in maintaining the ring's shape, despite individual stars having slightly varied orbital paths. However, this process typically causes gas to drift inward, which is not occurring in significant amounts, in this case, as evidenced by the empty core. Some astronomers suggest the ring might be self-regulating through feedback from star formation, the winds from newborn stars, and later, their supernova explosions can redistribute gas evenly throughout the ring. This action could maintain uniform star formation activity within the structure and prevent gas from accumulating in one area. The stars comprising the ring might be responsible for its long-term stability. Additionally, the ring's width is considerably smaller than its diameter. Its narrowness indicates that the orbital paths of its stars and gas clouds are very precisely aligned. In many other galaxies, the gravitational influence of nearby objects can tilt or stretch these orbits, causing the ring to thicken over time. The isolation of Hoag's object in space may be its greatest protection, allowing it to develop without the gravitational disturbances that would otherwise compromise its precision. Despite these factors, simulations of galactic dynamics frequently fail to generate a ring like that of Hoag's object, capable of lasting for billions of years. Most models show the ring either collapsing inward to form a disk or dispersing into a more chaotic configuration. This implies that Hoag's object may have formed under exceptionally favorable initial conditions, such as a perfectly balanced distribution of dark matter gas and stars from its inception, and has remained undisturbed since computer models are integral to modern astronomy for understanding galactic formation and evolution, but they consistently fail to replicate Hoag's object. These models apply established physical laws such as gravity gas movement, radiation, and dark matter behavior to simulate how galaxies operate. Over the past 2 decades, such simulations have successfully explained many galactic features, including spiral arms, starburst regions, and ring structures formed by collisions. The primary challenge is reproducing the galaxy's exceptional symmetry. Simulated rings, even in high-resolution models, typically appear slightly elliptical, clumpy, or tilted. Minor irregularities are expected because galaxies are chaotic systems where stars and gas react to numerous gravitational pulls from internal structures and neighboring objects. Hoag's object, by contrast, exhibits none of these anticipated distortions. The ring is so perfectly circular that even the most accurate models cannot replicate it without artificial data smoothing. The void between the core and the ring presents another significant challenge for simulations. Typically over hundreds of millions of years, gas and stars migrate inward from the ring, filling the gap and initiating new star formation nearer to the core. Similarly, galaxies such as the Cartwheel exhibit gaseous filaments connecting the outer ring to the central region. Hoag's object consistently defies this trend. In reality, the gap is nearly devoid of stars, whereas in simulations, it disappears rapidly unless specific conditions are imposed. Theories about its formation also face difficulties. In models based on collisions, a smaller galaxy passing through a larger one can create a ring structure through gravitational shock waves. This mechanism effectively explains galaxies with clumpy, irregular rings, but for Hoag's object, the simulations generate features like debris trails, asymmetrical arcs, or warps that are not observed. In resonance models where rings are formed by internal structures like bars, the lack of a bar in Hoag's object makes the required mathematics difficult to support. When the models are adjusted to exclude a bar, the simulated rings that result are typically unstable and dissipate over time. The composition of the gas introduces further complexity. The chemical makeup of the stars in the ring of Hoag's object does not align with the predictions of models for its proposed formation scenarios. Simulations generally assume the ring's formative gas originates from either the galaxy's primordial material or a captured companion galaxy. However, the metallicity profile of the stars in Hoag's object does not correspond well with either source. Incorporating these metallicity constraints into the models significantly reduces the probability of generating a ring similar to that of Hoag's object. The distribution of dark matter is another point of contention. A galaxy's dark matter halo shape and density profile are crucial in determining the stability of structures such as rings. In simulations, adjusting the halo to achieve the stability observed in Hoag's object often produces unrealistic side effects in other parts of the galaxy's structure. For example, a halo dense enough to stabilize the ring might also cause the core to rotate faster than observed or trigger excessive star formation, which would have resulted in a dustier and more irregular core. Even the most sophisticated multi-physics simulations, which integrate gravitational interactions, star formation feedback, and cosmic environmental effects, cannot create a galaxy that simultaneously matches all known properties of Hoag's object. The models may accurately replicate the ring, but fail on the core's smoothness, or they might produce a realistic gap. But with an elliptical ring, a trade-off always exists, suggesting the galaxy challenges physical laws to replicate it perfectly. The failure of these models does not imply that our understanding of galactic mechanics is incorrect, but rather highlights areas of incomplete knowledge. It is conceivable that Hoag's object formed from a set of initial conditions so rare they are not included in standard model parameters. Alternatively, a physical process not fully accounted for by current physics, such as an unusual interaction between dark and baryonic matter, might be at play. Hoag's object remains an anomaly in computational astrophysics. With each new set of model runs, astronomers look to see if this unique galaxy finally appears. Hoag's object is often discussed alongside other ring galaxies, but a comparison with its supposed counterparts reveals clear distinctions. To appreciate its rarity, it is necessary to examine cases such as the Cartwheel Galaxy AM 0644741 and the Lindsay-Chapley ring, which have rings formed through more conventional mechanisms. The Cartwheel Galaxy, located approximately 500 million light-years away, is likely the second most famous ring galaxy after Hoag's object. On initial observation, it resembles Hoag's object, featuring a bright outer ring surrounding a dimmer core. This resemblance, however, is superficial. The Cartwheel's ring was formed by a high-speed collision between two galaxies. A smaller galaxy passed through the larger galaxy's disk, creating shock waves that compressed gas and initiated star formation. This process left behind long, bright spokes of metal, a ring with non-uniform thickness, and fragments of metal scattered far from the main body. Hoag's object lacks any of these chaotic characteristics. An M0644741, also known as the Lindsay-Chapley ring, is another result of a collision. Its ring is thick and irregular, containing dense clumps, dominated by massive star-forming regions. Visible asymmetries are present caused by the non-uniform propagation of the shock wave through the galaxy's disk. In comparison, the ring of Hoag's object is smooth, uniformly bright, and so perfectly circular that no evident scars from a collision can be detected. This distinction is significant, as even the most idealized simulations of collision-formed rings yield some degree of distortion. For further comparison, one can examine polar ring galaxies, like NGC 4650A. In these systems, a ring composed of stars and gas orbits the main galaxy's disk at a significant angle. This configuration typically results from the accretion of material from another galaxy. While they can remain stable for billions of years, they nearly always exhibit a distinct bridge of gas, or a rippled transition zone where the captured material interacts with the host galaxy's disk. Hoag's object's ring is coplanar with its core's rotation. Analysts typically observe metallicity trends in other ring galaxies that are consistent with their formation mechanisms. In rings formed by impacts, the outer stars generally have higher metallicity because they are created from gas that has been compressed and enriched by recent starbursts. The metallicity of resonance rings, however, often matches that of the inner disk, as the gas is drawn in by the galaxy's internal structures, Hoag's object conforms to neither pattern. Its metallicity profile is unique and does not match the common formation models seen in similar galaxies. The dynamics of its ring also differ from other systems. In the Cartwheel and AM 06444741 galaxies, the ring is expanding as a direct consequence of a collision's shock wave. Observations of Hoag's object, however, indicate its ring is not expanding, but is in a stable long-term orbit around the core. This suggests a more deliberately formed structure rather than the outcome of a cosmic event. The isolation of Hoag's object is another distinguishing characteristic. Many known ring galaxies exist in environments with nearby galaxies, which increases the probability of the interactions that create rings. Hoag's object, however, resides in a relatively empty region of space, far from any large neighbors that could have recently disturbed it. This isolation makes a collision or gas capture scenario difficult to justify. Scientists struggle to classify Hoag's object. It lacks the morphology of an impact ring, the internal drivers of a resonance ring, and the alignment of a polar ring. It is therefore often placed in the broad category of a peculiar galaxy, designated for objects that defy standard classification. Hoag's object is distinctive, not because it has a ring which many galaxies do, but because its ring is of an unusual kind. Its construction, from its perfect symmetry to its chemical composition, cannot be explained through conventional means. When confronted with an object as unusual as Hoag's object, astronomers considered the simplest explanation, that it might not be a single galaxy at all. From our vantage point, it could appear to be two standard galaxies precisely aligned. This chance alignment theory proposes that the golden center is one galaxy, while the outer ring is another much more distant galaxy that appears to encircle the first due to the viewing angle. This idea is appealing as it would not require an exotic formation scenario, an explanation for the large, empty gap, or a reason for the apparent differences in color and age between the core and the ring. However, as astronomers tested this theory, it began to fail due to its improbability. The first issue is the alignment itself. For the core and ring to appear perfectly concentric, the centers of both galaxies would need to be positioned with extreme precision along our line of sight. A minor offset would cause the ring to look lopsided or distorted. The probability of two galaxies aligning in this manner, especially in a sparsely populated area of space like the one Hoag's object inhabits, is exceedingly low. The second problem relates to redshift measurements. Redshift, the stretching of light, due to the universe's expansion, correlates directly with a galaxy's distance. If the core and ring were separate galaxies, they would almost certainly exhibit different redshifts. However, when astronomers analyzed the spectra of both components, they discovered the redshift values were nearly identical. This means they are not just aligned visually, but are physically at the same distance, strongly suggesting they are part of the same gravitational system. The dynamics of the ring also present a challenge. Detailed observations show that the stars and gas in the ring are moving in a manner consistent with being gravitationally bound to the core. If the ring were a background galaxy, its stars would not be influenced by the core's mass and would not share its rotational pattern. The fact that they do indicates the core and ring are interacting in a way only possible if they belong to the same galaxy. The empty gap also contradicts the alignment hypothesis. One would expect to see faint indications of the background galaxy's internal structures, such as spiral arms, dust lanes, or star clusters, crossing the foreground core. The gap is completely dark, which is expected if it is truly empty space, and not just an area of overlapping projections. Some have attempted to preserve the chance alignment theory by suggesting the light from the background galaxy is being gravitationally lensed into a ring by the core. However, Hoag's object has insufficient mass to create such a perfect Einstein ring, and its visual features do not match those observed in actual lensing events. Beyond the physical evidence, the statistical odds diminish the theory's credibility. Astronomers have catalogued millions of galaxies, and while chance overlaps are not uncommon, perfect concentric alignments like this are virtually non-existent. To find one that also shares the same redshift, rotation dynamics, and isolation in space stretches the concept of coincidence beyond its limits. The chance alignment theory had been largely dismissed by professionals by the early 2000s. It is sometimes mentioned by those new to Hoag's object because it provides an interesting optical trick explanation, but upon closer inspection, its flaws become clear. The ring and the core are gravitationally connected. The formation of Hoag's object was not a coincidence, but an unusual phenomenon. To determine a galaxy's composition, its light is analyzed in addition to its shape. Using spectroscopy to separate its light into component bands, scientists can ascertain the chemical makeup, temperature, motion, and stellar age of Hoag's object. In most galaxies, the spectrum is fairly consistent across different regions. In Hoag's object, however, the spectra of the core and the ring are entirely different. The core's spectrum is dominated by light from older, cooler stars. It displays strong absorption lines from elements like magnesium and calcium, which are characteristic of an ancient stellar population that has been aging for billions of years. The relative absence of emission lines which signal hot glowing gas confirms that there is little to no ongoing star formation in the core. This is what one would expect from a golden elliptical-like center. The ring's spectrum, however, is completely different. Its light is bluer and hotter, with strong emission lines from hydrogen and oxygen. These lines indicate active ongoing star formation, with young, massive stars irradiating the surrounding gas with ultraviolet radiation. The oxygen lines also suggest the ring's gas has been enriched by multiple generations of stars, but the enrichment level is unusual, higher than in some galaxies of a similar size, but lower than what would be expected if the gas had been recycling through the core for billions of years. One of the most surprising discoveries from the spectral data is that the core and ring move at different speeds. Scientists use the Doppler shifts in spectral lines to determine how fast different parts of the galaxy are moving. In Hoag's object, the stars in the ring rotate much faster than the stars in the core, and the two components do not appear to be strongly dynamically connected. This is anomalous, as most galaxies feature a smooth transition in velocity between their inner and outer parts. The sharp discontinuity in Hoag's object suggests the ring and core may have formed through very different processes. Another strange finding from spectroscopy is the age difference between the two areas. Most stars in the ring are only a few billion years younger than the stars in the core. It appears the ring has undergone at least two separate bursts of star formation, one relatively recent, perhaps within the last billion years, and another that occurred much earlier. It is not yet understood why a stable ring structure would initiate star formation so long after the core had become inactive. The spectra also reveals something unusual about the gas in the ring. Typically, the gas that fuels star formation in a galaxy's outskirts originates either from the galaxy's own reservoir or is captured from intergalactic space. In both scenarios, the metallicity, the proportion of elements heavier than helium, follows a predictable pattern. In Hoag's object, However, the metallicity gradient does not make sense. The chemical composition of the ring's gas is inconsistent with an origin from the galaxy's core, yet it is also too enriched to have originated from pristine intergalactic gas. This discrepancy complicates the question of the ring's material source. Furthermore, certain spectral features are absent from both the core and the ring. For instance, indicators of shock-heated gas, typically found in galaxies that have experienced collisions or strong gravitational interactions, are either weak or absent. This observation aligns with other evidence, suggesting Hoag's object has not recently undergone a violent event. However, this also eliminates a significant potential mechanism for the ring's formation. These spectral characteristics demonstrate that Hoag's object is not merely a visual curiosity, but also a chemical and dynamical puzzle. The distinct nature of its old quiescent core and its younger star-forming ring challenges the conventional evolutionary connection between a galaxy's central and outer regions, presenting two seemingly unrelated narratives whose relationship is not understood. Infrared observations have confirmed the unusual appearance of Hoag's object and contributed to its enigmatic nature. While visible light reveals a galaxy's general structure, it does not provide a complete picture, as optical instruments cannot always detect dust-cooler stars or obscured star-forming regions. Longer wavelengths in infrared light allow astronomers to penetrate dust clouds and identify features missed by optical images. A primary infrared finding was the significant lack of dust emission from the core. Most galaxies, even those with very old cores, have some dust, and infrared wavelengths are particularly effective at detecting it. The core of Hoag's object, however, appeared nearly devoid of dust, supporting the optical view of a pristine central region. The absence of an infrared signature indicates that no significant amount of dust has been present in the recent past. Conversely, the ring presented a different scenario, with infrared images revealing strong signals from both dust and cooler, redder stars. This suggests that in addition to the young hot stars visible in optical light, the ring contains an older stellar population. The presence of this older component implies the ring has existed for longer than a single starburst event, challenging the hypothesis of it being a recent and transient structure. Infrared data also revealed insights into the distribution of star-forming regions. While appearing smooth in visible light, infrared observations detected subtle variations in brightness, indicating locations where new stars have heated cooler dust. These small hotspots reveal a pattern of activity not visible at optical wavelengths, suggesting a more complex history of star formation than previously assumed. Furthermore, infrared studies enabled an analysis of the metallicity of concealed stellar populations. By examining the different infrared spectral signatures of older and younger stars, it was found that the chemical composition varies significantly across different parts of the ring. This suggests multiple episodes of gas inflow over time, which could account for the varied metallicity without requiring a major collision. A significant discovery was made through deep infrared imaging of the space between the core and the ring. The observations confirmed that the gap remained almost completely dark, proving it is not an optical illusion caused by dust obscuration. The emptiness of this space is noteworthy because infrared images of other ring galaxies often reveal faint stellar bridges in such gaps, which are absent in Hoag's object. Infrared data also provided information on the ring's dynamics, verifying that it is in a stable long-term orbit, unlike the expanding rings generated by collisions. This stability supports the hypothesis that Hoag's object has sustained its unique structure for billions of years. Additionally, infrared images revealed a dim, extended halo of scattered light beyond the ring. This halo could be the remnant of an older, more expansive stellar ring, or an indicator of a dark matter distribution extending far beyond the galaxy's visible components. Infrared studies did not solve the puzzle of Hoag's object, but instead revealed that the galaxy is even more unusual than it appears in visible light. The stellar orbits in Hoag's object also present a problem. In most galaxies, gravitational pull and mass distribution result in predictable stellar motion, and observations typically align with these predictions. The stars in the outer ring of Hoag's object, however, deviate from expected models. When astronomers used Doppler shifts to measure orbital speeds in the ring, they found that although the velocities are generally consistent with the galaxy's total mass, they exhibit subtle, systematic deviations. The speeds fluctuate slightly rather than adhering to the flat rotation curve expected from a smooth, dark matter distribution. Such a wobble is atypical and suggests either an uneven distribution of mass or another influence on stellar motion. Another anomaly is the high degree of uniformity in the stars' orbits. In most galaxies, stellar orbits vary in shape, but the orbits within the ring of Hoag's object appear remarkably circular. Standard galactic models do not readily explain how such orbital precision could be achieved and maintained for billions of years. Simulations indicate that such perfect orbits are typically unstable over cosmic timescales, as minor perturbations should cause stars to drift. Yet there is no evidence of this occurring in Hoag's object. The ring has maintained its narrow width. Even the vertical motions of the stars, small oscillations above and below the ring's plane, do not align with predictions. The thinness of the ring suggests these vertical motions are suppressed more effectively than is typical, which could imply that the surrounding dark matter halo is exceptionally smooth and symmetrical. However, such a perfect halo would be uncommon. There is also a notable discrepancy between the motion of the gas and the stars in the ring. While the stars follow stable circular orbits, some gas clouds exhibit slight inward or outward motion and minor velocity variations, not expected in a perfectly balanced system. This indicates that the gas and stars are not responding to the galaxy's gravity identically. The stability of the ring's orbit might be attributable to resonance, a condition where the orbital periods of the stars have a simple numerical ratio with another rotating feature like the core or an undetected mass distribution. A resonance similar to how moons shepherd planetary rings can confine stars into narrow lanes. Hoag's object, however, lacks such a shepherding feature, and its core rotates too slowly to produce this effect. The absence of orbital drift is particularly perplexing given the galaxy's age. If the ring has existed for billions of years, it has withstood numerous potential disturbances, such as passing intergalactic clouds, the gravity of small unseen galaxies, and the gradual reshaping of its dark matter halo. Despite this, the orbits have remained pristine. This degree of stability suggests Hoag's object either formed and has remained in an exceptionally undisturbed environment or is stabilized by a yet undiscovered mechanism. Galaxies are not permanent. They merge, evolve, and expand over billions of years. The spiral, elliptical, and irregular galaxies observed today are largely the product of collisions, gas flows, and periods of star formation over long durations. Some scientists speculate that Hoag's object might be different, not a product of recent activity, but a fossil from the distant past. This hypothesis is based on the galaxy's unusual structure relative to its environment. Hoag's object is relatively isolated, distant from the dense galaxy clusters where mergers and transformations are common. Its smooth, dust-free core consists of older stars, suggesting long-term stability. The ring, though it now has younger stars, may have existed for most of the galaxy's life, with periodic star formation initiated by slow processes instead of violent events. Hoag's object may have formed during a vastly different cosmic era. In the first billion years after the Big Bang, galaxies were smaller, richer in gas, and prone to rapid bursts of star formation. If Hoag's object formed in a less dense region of space, it might have avoided the chaotic mergers that shaped other galaxies. It could have gradually settled into its core and ring structure and remained largely unchanged. Evidence for this theory is found in the metallicity, or the concentration of heavy elements of its stars. The core's high metallicity indicates a long history of star formation that enriched its gas early, followed by a sudden decline. The ring's metallicity is consistent with gas processed over billions of years without significant disturbance. This contrasts with younger ring galaxies, which frequently show evidence of newly acquired low metallicity material from external sources. If Hoag's object is a relic, this could also explain its near-perfect symmetry. Dynamically stable galaxies relax into smoother, more uniform shapes over eons, over cosmic timescales. Orbital irregularities of stars and gas smooth out, resulting in the geometric precision observed in the ring. Minor distortions from past gravitational interactions would have dissipated long before telescopic observation. However, this ancient origin theory faces the question of how the ring initially formed. The early universe is not thought to have produced such distinct large-scale rings without some form of interaction. One possibility is that Hoag's object began as a spiral galaxy whose outer arms evolved into a separate ring as gas moved outward and settled into resonant orbits. The spiral arms could have faded over billions of years, leaving the isolated ring. Another possibility is that Hoag's object is the remnant of an ancient gas-rich merger. Any debris from such a distant event would have since been absorbed or dispersed. In that scenario, gravitational waves passing through the galactic disk during the merger could have formed the ring, while the core remained intact. The disorganized remnants of such an event would become undetectable over time, giving the galaxy an undisturbed appearance. It is also suggested that the galaxy's dark matter halo may have helped preserve its ancient structure. A dense, smooth, and circular halo could have acted as a gravitational buffer, protecting the galaxy from tidal distortions for billions of years. This might explain why the seemingly fragile ring has not warped or fragmented. If Hoag's object is indeed a relic, it offers a rare view into a past era of galactic evolution. While most galaxies from that period have been reshaped beyond recognition, Hoag's object might be an exception. It could be a survivor from when the cosmic web was beginning to form its current structure of filaments and voids. This remains a theory, as there is no direct evidence of its ancient past, such as extremely old stellar populations in the ring or traces of primordial gas chemistry. It is certain, however, that if Hoag's object is an ancient galaxy, it is a remarkably well-preserved one that has been spinning slowly with perfect symmetry for a great length of time. Rare phenomena are expected in the universe where unusual alignments, extreme conditions, and peculiar forms can occur by chance. Hoag's object, however, pushes this assumption to its extreme. Astronomers have attempted to calculate the probability of a galaxy possessing a perfect ring, a perfect elliptical core, a large void matching redshifts, stable dynamics, and near-perfect symmetry. The resulting probabilities are almost absurdly small. Ring galaxies are inherently rare, with only about 1 in 1,000 local galaxies displaying a prominent ring, and most of these are the chaotic type formed by collisions. Perfect smooth rings, like the one in Hoag's object, are so rare that fewer than a dozen confirmed examples are known, none of which match its size proportions or isolation. The size ratio between the ring and the core further adds to its uniqueness. In Hoag's object, the ring's diameter is about 4 times that of the core, and the separating gap is proportionally vast compared to other known systems. This feature alone makes it unique, as no other recorded galaxy has such a large, clean gap between its central bulge and outer ring, without visible star or dust bridges. Its symmetry introduces another layer of improbability. Cosmic structures are seldom perfect circles, as gravitational interactions, uneven star formation, and random density fluctuations tend to distort them over time. The fact that Hoag's object has maintained such perfect geometry points to either a unique stabilizing mechanism or an incredibly tranquil history. Statistically, the probability of such symmetry enduring for billions of years without disruption is minuscule. Much lower than for a typical galaxy, the discrepancy in age between the core and the ring also contributes to its rarity. Most ring galaxies exhibit either similar stellar ages in both regions if formed concurrently, or clear signs of a recent event that rejuvenated one section. The stark contrast in Hoag's object, an old dormant core encircled by an active ring, implies that its formation process had to create this configuration and preserve it for an exceptionally long time. Modeling the probability of this sequence of events reduces the odds even more. If each unique characteristic of Hoag's object, perfect symmetry, a large empty gap, an old core with a young ring, no collision debris, isolation, and stable orbits, is considered an independent variable, and their probabilities are multiplied, the final number is too small to be expressed conventionally. Conservative estimates place the random chance of a galaxy having all these features at far less than 1 in a billion. Some astronomers warn that multiplying probabilities this way can be misleading, as the features may not be completely independent. For instance, an exceptionally stable formation environment could simultaneously increase the likelihood of both symmetry and stability. Yet even accounting for such correlations, the probability remains remarkably low. It seems as if the galaxy operates under a different set of cosmic rules. This improbability has prompted some researchers to question whether surveys are overlooking similar galaxies in distant or poorly imaged areas. However, deeper sky surveys have only confirmed its uniqueness. A few partial matches exist, galaxies with bright rings and faint centers, but none share its proportions, emptiness, or pristine structure. Hoag's object serves as a reminder to statisticians and astronomers that outliers can be so extreme they challenge existing models. Theories of galaxy formation suggest an object like this should be nearly impossible, yet it exists, indicating the theory requires reconsideration. This statistical anomaly does not imply the galaxy is supernatural or defies physics, but rather that it involves processes not yet understood or observed elsewhere. Hoag's object may not only be rare, but could also be the sole example of a galaxy formation pathway that was more prevalent in the past. This would make it both a time capsule and a statistical outlier. When the Hubble Space Telescope focused on Hoag's object in 2002, its objective was to obtain the most detailed image of its distinct ring, and core astronomers unexpectedly found a small, faint galaxy within the empty gap between the core and the ring. The galaxy is easily missed at first because it is small, dim, and aligned almost perfectly with Hoag's object, appearing as if intentionally placed. In the Hubble image, it resembles a small spiral galaxy, visible as an elongated smudge in an otherwise empty region. This discovery led to questions about whether it was connected to Hoag's object or was simply a coincidence. Speculation arose that if the smaller galaxy were gravitationally bound to Hoag's object, it could offer clues to the ring's formation. It might, for example, be the remnant core of another galaxy that interacted with Hoag's object, which could have triggered the ring's formation. If this were true, however, astronomers would expect to find tidal debris, such as faint streams of stars or gas connecting the two objects. Detailed imaging did not reveal any such material. The space between the small galaxy and the ring's inner edge is completely empty. Spectroscopic analysis provided a significant clue. By measuring the redshift of the small galaxy's light, astronomers concluded that it is not at the same distance as Hoag's object. It is, instead, a background galaxy located far behind it, viewed through the ring's central void. This explains the absence of interaction between the two, but it also makes the alignment seem remarkably coincidental. Some scientists have noted that from Earth background galaxies will inevitably be seen through other galaxies due to the vastness of space and intersecting lines of sight. However, for one to appear so precisely in the center of the ring of Hoag's object, a galaxy that is highly symmetrical and isolated, is considered strange even by experts. The background galaxy's shape also prompted interest. It seems to be a barred spiral, with a central bar of stars and two arms viewed almost face-on. This means its circular appearance in the image echoes the circular shape of Hoag's object's ring, making the alignment more striking. To a casual observer, it could appear as a galaxy within a galaxy, though they are separated by a great distance. Hubble's close-up view not only revealed this background galaxy, but also confirmed how empty the space between the core and ring is. Even at Hubble's resolution, no faint star clusters, gas clouds or dust lanes occupy the gap. This lack of material reinforces the concept that the ring and core are dynamically and structurally independent, with nothing linking them, a fact that continues to challenge formation theories. The small galaxy in the gap has since become a popular topic when Hubble's images are presented. For the public, it adds a cosmic bullseye feature that makes the sky seem stranger. For scientists, it is a reminder that the universe is three-dimensional and that redshift measurements are crucial for distinguishing between true connections and optical illusions. The background galaxy does not explain Hoag's object and appears unrelated to its structure, but its existence demonstrates how optical alignments in space can be so precise they seem intentional. It adds to the improbability of Hoag's object, as if one of the most unusual galaxies known required a small, strange feature within it to be even more mysterious. Studying tidal forces, the stretching and pulling from the gravity of other large nearby objects, is a primary method for scientists to determine if a galaxy's structure can endure for billions of years. These forces are a major factor in how most ring galaxies change shape, twist, or lose their coherence over time. Hoag's object, however, does not seem to adhere to these principles. Despite having a thin separate ring and a large empty space, it shows no signs of being bent, stretched, or disturbed by surrounding gravitational pulls. Galaxies are normally not truly isolated. Even in seemingly empty regions of the universe, they are part of larger gravitational networks that include dwarf companions, nearby spirals or ellipticals, and the influence of galaxy groups and clusters. These neighbors, whether near or millions of light years away, exert tidal forces that can subtly alter shapes over time. Rings can become oval, spiral arms can twist, and cores can become lopsided. The more fragile a structure, the more rapidly tidal forces can affect it. Hoag's object, however, exists in near-total isolation. Surveys of its vicinity have found no large galaxies within an influential range, and even small companions are scarce. This extreme solitude means external tidal forces are weaker than average, yet isolation alone does not explain everything, as the cosmic web itself applies a diffuse but measurable tidal influence. In most simulations, a galaxy with such a large and empty inner gap should be more susceptible to these subtle forces. With minimal material between the core and ring to stabilize the gravitational field, the outer ring should be more easily disturbed. Over hundreds of millions of years, it would be expected to drift inward warp or even break into clumps. However, observations show the ring's shape remains perfect, with no detectable warping or asymmetry. Another layer to the mystery is the interaction between the core's gravity and the ring's mass. In many galaxies, the stars and gas in a ring interact gravitationally with the central bulge, resulting in complex orbital patterns. If the balance is not perfect, tidal stresses from the core itself can cause parts of the ring to expand outward or collapse inward. For Hoag's object, the balance appears exceptionally precise, as if the core and ring are in a long-term gravitational equilibrium. This stability suggests the galaxy's dark matter halo may play a crucial role. If the halo is unusually smooth, spherical, and uniformly distributed, it could create a perfectly symmetrical gravitational environment that shields the ring from tidal distortion. Such a halo would effectively enclose the galaxy in a protective bubble, keeping the ring's orbit stable despite the absence of matter in the gap. However, such uniform halos are considered rare, making Hoag's object even more of an anomaly. The lack of tidal disruption also challenges the theory that Hoag's object resulted from a past collision. If it had formed from an interaction with another galaxy, tidal forces from that event should have left a lasting signature, such as a faint trail of stars, an off-center core, or uneven density in the ring. The complete absence of these features suggests that if a collision did happen, it must have been so ancient or so gentle that all traces have been erased, a scenario that is statistically improbable. Astronomers often conclude that without some form of ongoing, sustaining force, tidal forces should have altered the shape of Hoag's object over cosmic timescales. The fact that these changes have not occurred suggests that either key physics are missing from the models or Hoag's object exists in a very rare gravitational sweet spot. Determining a galaxy's mass is more complicated than simply adding up its visible stars. The great majority of a galaxy's mass is hidden, existing as dark matter or as gas and dust that are not luminous. Scientists ascertain a galaxy's total mass by measuring the speed of its stars and gas. The difference between this total mass and the mass of the visible matter is usually large but expected. This is not the case for Hoag's object. The disparity between its inferred mass and its visible light is so strange that it calls the measurements themselves into question. The starting point for measuring mass is the galaxy's rotation curve, which is a plot of the velocity of stars and gas at different distances from the center. In most galaxies, rotation speeds remain high, even far from the core, which implies the presence of a large dark matter halo. The rotational speeds of the ring in Hoag's object are consistent with the presence of significant mass beyond what is visible. However, when astronomers calculate the mass of the observable stars and gas, the figures do not align with the required mass. Hoag's object appears to have more total mass than its stellar brightness would suggest, yet less dark matter than would typically be needed to maintain such a large, thin ring for billions of years. This places the galaxy in an intermediate category where neither a standard dark matter model nor an explanation based solely on baryonic matter is sufficient. A portion of the galaxy's missing visible mass could be composed of dim, low-mass stars. One theory suggests that if these stars are old and evolved, they emit very little light, making them difficult to detect. A large population of such faint stars within the ring, coexisting with its younger and brighter stars, could increase the galaxy's mass without significantly increasing its overall luminosity. While infrared studies have hinted at this hidden population, the evidence is not sufficient to fully resolve the discrepancy. It is also plausible that the galaxy contains a substantial amount of cold gas that is not easily detectable at the wavelengths typically used to measure hydrogen. Neutral hydrogen is commonly detected via its 21-centimeter radial line, but this method may fail to register gas that is either extremely cold or in molecular form. This undetected gas could contribute to the galaxy's gravitational mass while remaining absent from standard measurements. Some researchers have also considered that the dark matter halo of Hoag's object might be shaped differently than those in other galaxies. If the halo were more concentrated toward the ring, rather than being evenly distributed, it could explain the ring's stability with less total dark matter. Such a configuration, however, is rarely seen in simulations, which tend to produce smoother halos that are less influenced by specific formation events. The problem of the hidden mass is further complicated by the galaxy's isolation. Without nearby galaxies to exchange mass with, the mass distribution of Hoag's object should be relatively straightforward, yet the measurements defy simple classification. Some teams have proposed that our standard assumptions about the mass-to-light ratio may not apply here, and that the processes that formed Hoag's object resulted in a fundamentally different ratio than that of most galaxies. If true, this would imply that Hoag's object is more than just a structural curiosity, and that our models of galaxy formation may be missing a critical variable, particularly concerning how mass is distributed among stars, gas, and dark matter. It is possible that galaxies can form with dark matter halos that arrange matter in unusual ways, creating the stable, symmetric rings observed. The forms, structures, and stellar populations of galaxies evolve over millions or billions of years. While some morphologies, like classic spirals or giant ellipticals, are stable for long cosmic periods, others are transient configurations that exist for a short time before being altered by gravity. This raises the possibility that Hoag's object represents such a short-lived phase, a brief cosmic arrangement observed at a particular moment. This hypothesis is founded on the idea that the ring of Hoag's object, despite its apparent stability, may not be a permanent feature. Computer simulations of ring galaxies, especially those with a disconnected core and ring, often indicate that the ring either migrates inward or dissipates over time. If the stars in the ring of Hoag's object are slowly drifting, the ring could lose its perfect equilibrium. If this is the case, we may be observing the galaxy during an optimal period in its evolution, long after its formation, for the ring to have settled into a clean shape. But before the forces that disrupt such structures have taken full effect, this window might last only a few 100 million years, a fraction of the galaxy's total age, making its observation now a matter of astronomical luck. A variant of the transient theory suggests the ring could be a residual wave from a past disturbance, such as an interaction with a small galaxy or an internal burst of star formation which created a gravitational ripple that pushed gas and stars outward. Over time, this wave would diminish and the ring would lose its structure. If Hoag's object is in the midst of this process, we may be viewing a phase that is nearing its end. Alternatively, the galaxy could be temporarily accreting gas from its surroundings. A filament of gas that fell toward Hoag's object in the past could have been captured in a stable orbit that is now fueling star formation in the ring. This gas supply would eventually be exhausted, causing star formation to slow and the ring to fade. The transient idea also connects to the age difference between the core and the ring. If the ring's stars are relatively young compared to the core, the current configuration cannot have existed for the galaxy's entire history, meaning the ring either formed recently or was rejuvenated by an influx of material. In either scenario, its present form is temporary. The appeal of this theory is that many of the strange features of Hoag's object, the sharp separation, the absence of connecting structures, the perfect symmetry, might be side effects of observing it during a rare, short-lived stage. In a billion years, it might look entirely different. However, this explanation faces challenges. The ring's stability appears unusually high for a temporary structure, and measurements of stellar motions suggest it is not in immediate danger of falling apart. Furthermore, no clear evidence of a triggering event, such as debris or distorted gas clouds, has been found. If Hoag's object is indeed transient, its observation is highly fortunate and suggests that while other such galaxies may exist, only a few would be visible in this phase at any given time, explaining why so few close analogues have been found. Scientific puzzles typically become less mysterious over time, as improved technology and models allow objects to be explained by existing theories. Hoag's object has not followed this trend and remains one of the most debated galaxies after decades of research. The lack of consensus stems not from a shortage of data, but from the fact that the data do not fit neatly into any single theory. Several theories exist, including collision models, resonance wave models, and ancient relic scenarios, but each one explains some features of Hoag's object while contradicting others. For example, the collision model explains the core ring separation, but not the lack of debris. Resonance models explain the symmetry, but struggle with the age difference between the core and ring. The early universe relic theory works for the core's properties, but not the ring's ongoing star formation. This problem of partial fits has led to a scientific stalemate. The galaxy has become a stress test for formation theories. Any model that could fully explain Hoag's object would be considered exceptionally robust, but so far, no model has succeeded. The challenge is amplified by the galaxy's rarity. Astronomers identify trends by comparing many similar objects, but true analogues to Hoag's object are too uncommon to form a statistical sample. When a potential match is found, closer inspection reveals key differences, such as a warped ring or an off-center core. Advanced technology has provided more details, but has not delivered the conclusive evidence needed to settle the debate. Hubble's high-resolution images in 2002 confirmed the galaxy's near-perfect symmetry and empty gap, deepening the mystery. Radio and infrared surveys have offered clues about its gas and hidden stars, but no findings have been decisive. The lack of agreement is not just a technical problem, it is a conceptual one. Astronomers are accustomed to working within frameworks that explain most galaxies as products of common cosmic processes, like gravity mergers and internal star formation cycles. The unique characteristics of Hoag's object imply that either a rare but normal galaxy formation process is yet to be discovered, or that the adaptability of current galaxy models must be reconsidered. Some experts suggest the solution may be found through currently unobservable means, proposing that extreme ultraviolet X-ray or gravitational wave observations could reveal more about the galaxy's history or find hidden patterns in its dark matter ring. Others anticipate that next-generation telescopes, like the Extremely Large Telescope or the Nancy Grace Roman Space Telescope, will detect very faint objects or subtle variations that could explain the object's origins. For now, Hoag's object serves as a case study in scientific patience and a reminder that not all puzzles can be solved quickly, despite rapid technological progress. The galaxy remains in cosmic isolation, offering no new information to resolve the decades-long arguments among astronomers. It persists as a perfect ring in the darkness, defying every explanation offered. Its code may one day be broken,